Alright, hello students. Welcome back to another video lecture for ComSci 191, Computer and Network Security. Supposedly this should be a live session, but some students were not able to attend, so we're just going to record the video. Okay, so today we're going to talk about encryption. And our main reference for this video, for this lecture, is chapter 2 and chapter 20 of Stalling's textbook. So let's get started with chapter 2, which is a brief introduction of cryptographic tools for computer security. So this is our main reference. Objectives at the end of this chapter: you should be able to describe symmetric encryption and asymmetric encryption. So what do we mean by encryption? So encryption is important when it comes to security because for confidentiality purposes. So we don't want our data to be read or to be accessible by others who are not supposed to access the data. And the way the encryption works is using some, as shown here, some substitutions and transformations. Let me check. My system is not okay. Let me pause this video recording. Okay, so let's go back, let's continue. So symmetric encryption works by having a shared key, which is shared by both the sender and the receiver. And we have a plain text input, X, and it is passed through an encryption algorithm, let's say data encryption standard. And what DES does is to perform some substitution and transformation, and then after that we're going to get the ciphertext, which denote as Y, and this we have the encryption as algorithm as a function of two inputs, the key and the plain text. Then this will be transmitted to the receiver. And at the recipient end, we're going to have a key, the same key as the sender, and then it will be run to the decryption algorithm, which is the reverse of the encryption algorithm, to retrieve the plain text output. So you have the plain text here, and you have the decryption algorithm, you have the same key, and you have the ciphertext. So that's the basic idea behind symmetric encryption. Now, given for symmetric encryption, what are the two requirements for this to work? So the first one is the opponent should not be able to decrypt ciphertext or discover the key. So two approaches to attack symmetric encryption: decrypt the ciphertext or discover the key, even if he or she is in possession of ciphertext with plain text that produce its ciphertext. So that's the idea. As an attacker, my goal is to be able, one, is to decipher actually the ciphertext, to get the plain text out of the ciphertext. So, and in order to do that, the first approach is to get the key, because if I know the key, then I can decrypt the ciphertext. Okay? And how am I going to derive the key? if it's possible, if the algorithm is weak, the attacker can have plain text and ciphertext pairs, and it's possible that the attacker might be able to deduce or extract the key from these plain text ciphertext pairs. The second requirement is that the sender and the receiver must obtain the key in a secure fashion. So this is a question of key distribution. Since the key are shared, how does the sender give to the receiver the key? Right? So that's main requirement. So the keys should be distributed in a secure manner. If any of these two fails, then symmetric encryption will not work. Now, how do you attack symmetric encryption? There are two approaches. We have cryptanalysis and brute force attack. In cryptanalysis, you need to have an understanding of the algorithm, of the encryption algorithm, then plus some knowledge of plain text characteristics. For example, what characters are used in the plain text, is it using the English language, etc. And then the attacker can have some access to plain text, ciphertext pairs, as I mentioned earlier. And then the attacker will exploit the characteristics of the algorithm to deduce the specific plain text or the key. So in this example, you are given, it's possible that the attacker will just like to get the plain text of a given ciphertext. Okay? So that's cryptanalysis. So it's more on theoretical and analytical study. The second attack is the brute force attack. So remember that in the symmetric encryption, you have the key. So normally the key is represented as bits, right? And since these are bit patterns, let's say 1011, you can try all the possible combinations of the keys to obtain the key. Now, if say we only have 4 bits to represent the key, it's very easy to brute force or to try all possible combinations of the bit patterns for the key to be able to derive the key. So the attacker will try all possible keys on some ciphertext until it gets an intelligible translation into plain text. So it can be done. Statistically, on average, half of possible keys must be tried to be able to perform a brute force attack. So this is commonly there are other brute force attacks, but count takeover, for example, can be done using brute force attacks. So this table it describes or illustrates the exhaustive key search. And as I mentioned, the keys are usually represented as bits and their length is called the key size. If the size or the key size is 32 bits, then there are 2 to the 32 possible combinations or permutation or combinations that you need to try, and this will be the equivalent for that. And then if you have a system that can perform decryption, one decryption per microsecond, if the key size is 32 bits, then it will take 35.8 minutes only. But if you have a high-end machine, for example, that can perform the decryption operation at 10 to the 6 the decryption per microsecond, then you have a very fast, you can brute force the key in this short period of time. So the trick is you should increase the key size. in terms of bits, because you can see, even though you have a high-end machine, this will be the time it will take to extract the key by trying all possible keys based on the combination of the bit patterns, right? Now, when it comes to symmetric encryption, there are actually two ways to do this. We have block cipher and stream cipher. In the block cipher, we process the plain text input in fixed size blocks and produces a block of cipher text of equal size for each plain text block. So that's why it's called a block cipher, because the processing is done in blocks. For example, we have DES, triple DES, and AES. The plain text or the block size, the plain text block size for DES is 64 bits, triple DES 64 bits, for AES 128 bits. Then the output size, okay, same as the plain text size, cipher text size. And then the key size for DES is 56 bits only. For triple DES, we have 112 or 168 bits, and for AES, we have this key length. So remember that the longer, the better, because it's very hard. It's harder to brute force. So let's talk about a popular or an old block cipher called DES. So as described previously, it uses 64-bit plain text, 56-bit key, and 64-bit cipher blocks. Now, DES, the main issues with DES is that if you study the algorithm, it's possible to do cryptanalysis and be able to obtain the key or the plain text of a given ciphertext. And also, since the key size is 56 bits only, it's quite easy to guess if you have a high-end machine. In fact, DES is no longer used today because it's already cracked. Meaning, there are tools that can actually crack DES encrypted data. So this is a set of statistics for an exhaustive key search, brute force attack, and you see the differences among the different these different block ciphers. Okay, so you see the AES here with this key size, and it will take a long time to do an exhaustive search given this a machine with these properties. Then triple DES, so it repeats the basic DES algorithm 3 times. It's using either 2 or 3 unique keys. We'll discuss this in chapter 20 of the textbook. Key length, okay. So it's actually much more secure, but it's slower because it calls DES algorithm 3 times. And the block size is still 64 bits, and ideally the larger the block size, the larger block size is desirable. Advanced encryption standard. So AES is the modern, or the one we use today. It is a better replacement for DES. It was in 2001 that the Reindel was selected as the algorithm for the AES, and this is a symmetric block cipher, and these are the properties of this cipher, and is now widely available commercially. AES is used in some ransomware to encrypt when a ransomware hits your system. It will encrypt all the files using symmetric encryption. AES is actually used to do that in some ransomware variants. Okay, so this figure here illustrates the difference between block cipher and stream cipher. So as I said, block cipher, the encryption is done by blocks, whereas in the stream cipher, the encryption is done by byte stream. So let's look at the first figure. So this is an example of a block cipher system using what we call an electronic code book mode, ECM mode, ECB mode, actually ECB mode. Okay. In block ciphers, we have different modes of operation, which we will discuss later, but the basic one is called the ECB mode. And this is how it's done. So your plain text is divided into blocks. In this case, there are n blocks. So let's say in the case of DES, the block size is 64 bits. So this means that each of these blocks is 64 bits. Then you have the key, and you have the encryption algorithm that will encrypt this plain text using this key, and you get ciphertext. So B here is the block size. So in the case of DES, this is 64 bits, and you get n blocks of ciphertext, which can then be concatenated to form the final ciphertext. For the decryption process, so it's just the opposite. So you are given the different blocks of the ciphertext, then you perform the decryption algorithm using the key, and you get the plain text, and then you concatenate them, then you get the original plain text. For the stream encryption, okay, so the idea here is the plain text is treated as a byte stream n, meaning it's just an array of bytes. There is no blocking done as an error. So the idea is the key is used as an input in a pseudo-random byte generator, or called the key string generator, and that the result of that key string generator, denoted here as a small k, is XORed with the byte stream. So it can be a bit or it can be a byte, and then this is used to encrypt the XORed actually with the bytes that are coming in the encryption. So that's stream cipher. Okay, so here are the properties. Okay, for the stream cipher, it encrypts 1 byte or 1 bit at a time. So as I mentioned, this small k here can either be a byte or a bit. It's faster than block cipher, and keys cannot be reused because of this generator. Right? So it's possible to generate the it may be the case that the same key can be generated, so reuse of the key is not allowed. Okay, so those are the two symmetric encryption. So another concept in cryptography is called message authentication. Symmetric encryption is more on achieving confidentiality of information. So let's encrypt this plain text data so that Alice will encrypt the plain text data so that the attacker will not be able to read the data. That's confidentiality. So we also have the concept of authentication. So we want to make sure that the message is authentic. So asymmetric encryption is against passive attacks, like being able to read the contents of a file, whereas authentication is protection against active attack, like data falsification. So you want to know that the received message is authentic. When we say authentic, that means the contents have not been altered. It is from an authentic source and the timely and incorrect sequence. So this is very important nowadays, since we are most people are working from home. Example, signing of PDF documents, signing of forms. How do you know that even though I attach my signature specimen on the PDF document, that document really came from me? How do you do that? So cryptography has a tool for that. It's called message authentication and hash function, which is basically used for authentication. And to do this, to accomplish this message authentication, you can actually use conventional encryption, symmetric encryption, but still limited. And the main idea of why this works, why the original or the traditional or conventional encryption works for authentication, is as long as the sender and the receiver are the only individuals or entities that has access to the shared key, then it is guaranteed that the message is authentic if it is guaranteed that the sender and the receiver only are the ones who have access to the key. So another approach is to actually don't use encryption for authentication. Use a different mechanism for authentication. And the way to do that is to append an authentication tag to the plain text message. Okay, we have the plain text message. Then we're going to attach a tag to this plain text message, and that is called an authentication tag. And traditionally, the plain text message itself is not encrypted. So this means that if you are only interested in authentication, there is no need to encrypt. Okay, we just add a tag to the plain text message. Although it is still possible that to both encrypt and add a tag, so a combination of both. We'll have an example later. So some reasons why the plain text message is not encrypted are the following. So the same message is broadcast to several destinations, so there's no need to let everyone do the decryption of the message. Just let one entity to do the authentication and just send the message to the rest. One end has heavy load, thus cannot encrypt and decrypt. So it's possible that one node in a network, for example, cannot perform the decryption and encryption. So it's better to just send it the plain text so that it will no longer perform encryption and decryption. Or there is really no need for encryption. Why bother? So let's just use an authentication tag. So this is actually how it works. We have in security, you will often hear the word MAC or MAC. So it's called Message Authentication Code. So how does this work? First, we have the MAC algorithm, message authentication code algorithm, and as input to this MAC algorithm is the message and also a key, a key K. And then the output of the algorithm or the MAC algorithm will be a message authentication code, and this will be appended to the plain text, and this will be transmitted across the network. And at the receiver end, the receiver, let's say this is Alice, this is Bob. So when Alice sends data to Bob, Bob will receive this piece of data. So what Bob's going to do is to extract the message, and then since Bob knows the key also from Alice for the map, it will generate a map, and then it will simply compare the two maps. If they are the same, then this means that the message is authentic. So that's pretty neat when it comes to authentication. So message authentication codes, if only the sender and the receiver knows K and the received code knows the computed code, then the receiver is sure that the message has not been altered, because otherwise it will generate a different map at the receiver end, or tag or map. The message came from the sender because K, and the message is in proper sequence, because if embedded is in the message is a sequence number, for example for TCP segments, then if the sequence is altered, then it will generate a different map at the receiver end. So the question now is, what is this MAC algorithm? How do we use this? So a common approach is to generate the code. To generate the code is to encrypt the message K using DES as described earlier, and use the last 16 or 32 bits of the ciphertext as the code. So that means this will be a DES. You run DES here, and then you extract the last 16 bits or 32 bits of the ciphertext, and that will be the map. Okay, this will be the map. Okay. Now, if you don't want to use encryption to generate the map, we can use what we call hash functions. So you are familiar with this already when in ComSci 123, when you have the hash table, and in the hash table data structure, you have a hash function which generates an index to the array. So it is very similar to that. So the idea of the hash function is you have a message M or data block M, which can be variable in length, right? And if you feed that to a hash function, it will generate a hash value of hash called hash fixed length hash, and you can use this as the message authentication code. Okay. Normally you do this when you download ISO files or other data and you would like to check whether the data is valid. Okay, so you usually have a hash for that. For example, malware samples. Some malware samples is fed. For example, this is an executable of a malware. Say this is a malware, and then you feed that the data or the executable of that malware to the hash function, and it will generate a SHA-256 hash, probably, that uniquely identifies this malware sample. So the idea is you have a fixed, the output is a fixed size message, okay, and if it's usually padded out to generate to make it a multiple of integer multiple of certain bits or values, and the paddings includes the original length of the message, and the secret key is not needed. So there's no secret key in this when you use the hash function. So it's all embedded in the algorithm itself. So here is 3 illustrations of how to do message authentication using one-way hash function. So first we have using symmetric encryption. So we have the source, we have the destination. So the original message is passed to a hash function, and it will generate a fixed size block, and then it will be encrypted using a key, and then the encrypted hash will be used as the MAC, and that will be transmitted to the destination. Another approach is to use a public key encryption, wherein the message again is passed through a hash function, and it will get this hash code here, and then it will be encrypted using the private key of the sender, and it will be generate a MAC that will be transferred across the network, for example, and then at the receiver end, the original message is passed to the hash function, and then this one here is decrypted using the public key of the receiver, and then it will compare whether the MAC is the same as the decrypted one here. And another one is using a secret value. So the original message is sandwiched between some secret K, and then taken together, passed to a hash function to generate the MAC, and then use that as the MAC for the message, and then transmit across the link, and then from there extract, then compare again to check whether the message is authentic. Okay, so these are the approaches using the hash function for message authentication. So some characteristics of the hash function requirement. So the idea here is that the hash function can be applied to any size data. H produces a fixed length output, and h of x is relatively easy to compute for any given x for both hardware and software implementation. So these are the main requirements if you're going to use a hash function. No, we have more actually. So the fourth requirement is pre-image resistant or one-way property. So given the code H, okay, this is the hash code or the hash, it should be computationally infeasible to find X, the original one, such that H of X equals H. So given the hash code, you should not be able to obtain the value of that particular, the original value or data from which the hash code was derived. The fifth one is called weak collision resistance or second pre-imaging. So here you are given the black X. So this is the original data that you would like to compute the hash for. It should be computationally infeasible to find Y not equal to X, such that the hash of Y is equal to the hash of X. So it should be difficult to do that. So it guarantees it is impossible to find an alternative message with the same hash value as a given message. For example, you have a document that says you're giving away or you're paying some large amount of money, and if you can generate the same hash and you change the amount to some other values, then this is a violation of the this hash function property. And the last one is actually the sixth requirement: strong collision resistance. So it should be computationally infeasible to find a pair X and Y data such that the hash of X is equal to the hash of Y. So there's a difference between this weak collision resistance and this strong collision resistance. So here it says any pair, right? So you have to be able to prove that any pair will not generate the same hash. Nowadays there are some studies, actually in MD5 for example, in the seed labs we have the MD5 collision lab, wherein different sets of data, different X and Y, they generate the same hash code. Okay? It's in the case of MD5, the MD5 algorithm. So nowadays MD5 is actually no longer used. So it's used when one party generates a message for another party to sign. Okay, so that's hash function. So how do we attack hash functions? So to attack hash functions, we have the same technique for symmetric encryption. We can do so using cryptanalysis, and the other one is by brute force. So cryptanalysis, you study the logical weakness in the algorithm. So this is the case of MD5. So in the case of MD5, they were able to show that given two X and Y, they generate the same MD5 hash by analyzing the MD5 algorithm, or via brute force. So you can try many inputs. Okay. So the strength proportional to the length of the hash code should be like this. So it's very difficult actually to try to brute force this, because you have a high search space, big search space. So what is the widely used hash algorithm? We have the SHA algorithm. It's the most widely used hash algorithm. It gives SHA-1, it has several versions. SHA-1 gives 160-bit hash. They have SHA-2, SHA-2 have SHA-256, SHA-284, and SHA-512. And the latest is SHA-3, so secure hash algorithm for hashing. Other applications of hash functions, we have passwords, or hash or password is stored rather than the password. So it's very important when you write your web applications. If you allow your users to register to your system, you don't store their password on your database. You have to hash the password, add some salt in the hash process, and then you store the hash in the database. So let's have an example of this. Let's take a look at an example. Oh, I haven't set the VM. Anyway, I'll show the example to you later after this discussion. I failed to set up the VM, the scene for the VM. Anyway, so I'll show this later. And intrusion detection, you store the hash value of files in the OS. This is, for example, we have a tool called check rootkit. So there's a kind of malware called rootkit that tries to replace the system binaries in a system or in an OS. So to be able to detect changes in the system binaries or libraries, you can store the hash of the system binaries, and then from time to time recompute the hash of the system and then compare it with the stored one to detect whether the original binaries were replaced. Okay. So we'll stop on this slide, but we'll have part 2 in the next video.